So everything is all right now, sir?
Yeah.
Yeah. No.
Good morning, professors.
Good morning.
So live streaming has started in the YouTube now. So we'll start in another 1 or 2 minutes time.
Go to the. I have to press this.
No, stop.
Stop. I stopped already.
Yeah.
So go to the app. What was that?
Just press the background.
No, I still don't know exactly how to do. Just press the background. Every time I got
it.
Yeah, now I got this, but I don't know how to flip now. Again, I have to go pop screen.
You have to go to PowerPoint.
Yeah, I have to present. After that, I have to answer questions. Now I have to come here, so I don't know how to come back.
No, you can't come. You have to hear the voices of the people and answer.
No. Here, question and answers window is there. I have to press this and then answer the questions.
So,
You will have to switch alternative.
Just tell me
sir,
one more.
So mute the audio and video, sir.
Okay.
So we'll start the session soon. Please wait. So shall we start, sir? Professor, shall we start?
Yeah, I think we can start now.
Yes, sir. Yes, sir. So, very good morning and hearty welcome our distinguished speakers and all the participants to the last day of our webinar. And Professor Murthy, Professor Rikukan, Professor Jaya, Professor Satish Kumar, and Professor Ruben Goswami, and all the participants and my dear colleagues. And so, please welcome all of you and all the participants, those who are viewing through the YouTube and live streaming and through the Zoom platform. So, welcome you all. So, today Dr. Satish Kumar will be addressing on the impact of seismic code provisions on seismic design of steel buildings. And Dr. Satish Kumar is a professor of civil engineering, structural engineering division, IIT Madras. He obtained his PhD from Nagoya University, Japan during 1996. And he has been with IIT Madras since 2013. And his expertise are in design of steel structures, hot rolled and cold formed steel, and steel concrete composites, earthquake resistant structural design, masonry, RC, and steel, and fatigue and fracture and steel. So we are eagerly waiting for your lecture, sir. And today, at the end of the session, we will have a panel discussion. So all the participants are requested to stay back until the end of the session. So instead of asking for the materials, you please listen to the lecture and the concluding remarks by the distinguished speakers as an outcome of the deliberations. So now we can start the session, sir. Professor Satish Kumar, sir. Now you can start, sir. Presentation is already in the screen. Sir, I think audio is mute, sir. You're not able to hear. I think sir is facing some problem with the iPad.
She muted actually. What's that? Okay.
And now we can start, sir.
Okay.
Okay, sir.
But my screen broadcast. Okay,
sir.
good morning.
Okay. Thank you, sir.
So basically, we are going to look at earthquake resistant structures in steel today. And the presentation will be like this. Basically, I'll be talking about seismic analysis and design as applicable to design of steel structures. Some of these issues and topics have already been covered by other speakers, but I'll be touching upon the specific aspects related to steel. And then I'll look at design and detailing for earthquake loads as given in the provisions of the IS800 section 12, which is the, right now we can call it as the code for design and detailing for steel structures for earthquake loads. And then I'll be just giving a quick overview of some special systems which are quite common in other countries, but have yet to take off in our country. So with that background, I'll just go to the design philosophy. Basically, a variety of issues have been told about seismic design, but like performance-based design, having multiple performance objectives and all. But the basic core of seismic design is what is known as a dual strategy. There is only two performance objectives. One is to ensure elastic behavior under a moderate earthquake, and the other one is to prevent collapse under a severe earthquake. As of now, even these objectives, we are not able to clearly meet due to the various uncertainties in the demand and supply, both sides of the spectrum. So this itself is a very big issue, and I'll explain how we try to do this. So basically, we estimate based on the probability of occurrence, etc., which Professor Raghukant covered yesterday. We estimate the design seismic load. Okay, that is basically, it could be estimated as a ground motion, then converted into a response spectrum, from which we pick up the base shear and the distribution of base shear over the height using principles of structural dynamics. And then based on these loads, we apply these loads in a software. We model the structure in a software, apply these loads, and we do actually what is called as an elastic analysis. So we do this elastic analysis and ensure that the stresses don't go beyond the yield limit. Okay, so that is one level of analysis. The other one that we want to achieve is to prevent collapse under a severe earthquake. For this, we talk of properties like ductility, which are even more difficult to estimate. And also we should remember that the inelastic behavior of structures is not easy to estimate unless we do a nonlinear analysis. And so currently that is not being done, and the codes prescribe design and detailing rules, which it says that if you follow, these are based on capacity design principles. And the code says that if you follow this, then you would be able to prevent collapse under a severe earthquake. So that is how we look at it. And so whatever you do for reinforced concrete as per IS456, applying the earthquake loads to the system, that would be the first one, that is ensuring elastic behavior under moderate earthquake. And the second one, whatever you do as per IS13920, that would be the second one. So in steel also, whatever we do as design using basic IS800 provisions, that would be the first level of ensuring elastic behavior. And the second one would be designing and detailing as per section 12 of the code to prevent collapse under a severe earthquake. So the second strategy does not involve any calculations. So you don't calculate the ductility or you don't calculate the energy dissipation capacity, etc. But we just try to maximize it and then hope that that will be adequate to ensure safety under a severe earthquake. So that is how it is done. And we understand that collapse can be due to excessive deformation and consequent instability of the structure, could be like overturning, etc., etc. Or it could be due to loss of strength and stiffness, be due to what we call as damage to the structural elements, members, connections, etc. So these are the possible ways in which a structure can collapse. As far as the elastic resistance is concerned, we depend on the yield strength and initial stiffness. So these are easy to calculate. So we use these and we actually can prove mathematically that the structure has adequate elastic resistance. As far as inelastic resistance is concerned, we are talking in terms of the stability beyond the elastic limit, or it could be sometimes within the elastic limit, but then actually the elastic limit gets blurred due to initial stresses, deformations, imperfections, etc., etc. So we are talking in terms of stability, ductility, and energy dissipation capacity to assure us the inelastic resistance is adequate for a possible severe earthquake. Okay, so that is how we go about. And we do have some drift limitations also in the codes, which we, to satisfy which we need to ensure adequate stiffness so that we are able to control the drift. This drift limitations can help us to control the non-structural damage. Okay, and regarding the inelastic earthquake resistant properties, we have already been these have already been explained. That ductility is a property wherein it allows large plastic deformations without significant loss of strength. Okay, there might be some loss of strength, but that should not be very significant. Similarly, the hysteretic energy dissipation capacity allows energy dissipation without loss of strength and stiffness. So these are the two properties that help us in doing it. Okay, so what are the advantages of steel for earthquake as a material for earthquake resistance or as a material of construction. So basically, it is by nature it is very ductile and consequently gives robust structures. So that could be redistribution of stresses, that could be redistribution of moments. So whenever one section of a steel member reaches its ultimate, let's say what is called as the full plastic movement, it develops what is called as the plastic hinge, and it continues to rotate until other sections of the member also reach their limit. Okay, so basically that is redistribution of moments, and that gives a very robustness. Robustness is defined as the ability to survive or avoid collapse even under some degree of damage at certain locations. Okay, so the other advantage we have with steel is it can withstand reversal of stresses. So mostly the stresses that it is able to take in tension and compression, that is the stress strain curve for steel in these two directions are almost the same, unlike concrete where it is pretty much weak in tension, right? So in fact, you should remember that in reinforced concrete also we do use lots of steel, right? So to achieve ductility and energy dissipation, etc., etc. So that is another major advantage. So I don't need to probably design a section which has been designed for, let's say, sagging bending movement. It will be able to take considerable amount of hogging bending movement, or a member like a column which is under compression can take considerable amount of tension, right, without having any serious issues. So that is another advantage. It can dissipate considerable amount of energy under cyclic loading. So that gives the enormous robustness to the structure. And it is whatever basically the Professor Sivyamurthy has told you that earthquake comes as a base motion, and this base motion translates into a inertia force which takes the structure beyond the elastic limit, and then under such cyclic loading the structure will be able to dissipate the energy. The energy that is input by the earthquake into the structure can be dissipated, and thereby the structure is able to survive the earthquake, right? So that is another major property. Then steel is produced under considerable quality control, and its behavior is well documented. So it very much suits what is known as capacity design. So when we say that a particular section is going to yield at a particular moment or load, it does yield at that load. Okay, so that is another major advantage that we have, except for some minor overstrength which we build into our design, right, as a safety factor. So the major advantage of steel is that it also gives light and flexible structures. You know that the seismic load is basically an inertia force, which is mass into acceleration, right? So if we can reduce the mass and if we can reduce the acceleration that is experienced by the structure due to a particular peak ground motion or peak ground motion of certain peak ground values, so then we would be able to reduce the seismic load itself, which is a very big advantage for us. So steel being a high strength to weight ratio material, so for example, steel normally it has a yield strength of 250 MPa if it's my steel, but we are able to now produce steel of the order of even 1000 MPa yield strength. So it does have very high strength, so which means that you will need very little material in your structure to take the loads. Okay, so consequently, there is a weight reduction in the structure. Weight reduction is basically nothing but a reduction in the mass of the structure, which translates directly into a reduction in the inertia force. Okay, also being a high strength material, it requires less cross-sectional areas, and thus consequently, which will translate into less moments of inertia. So, which in turn translates into a flexible structure. So we have seen the response spectrum, how as the time period increases, the what do you call the base shear or the coefficient, seismic coefficient comes down. So accordingly, we would get a reduction in the spectral accelerations also. So we get a reduction in mass, we get a reduction in the spectral acceleration. So we get a double reduction in the seismic load. So generally, as a consequence of this, most structures that we design may not be even governed by earthquake loads in that sense. Okay, so we would find that other loads like wind loads, etc., might govern, and the seismic loads may not be governing, but this doesn't mean that the seismic load cannot exceed what we have considered. It can, and then in that case, the inelastic properties of the structure will come in, right? So that is how it is. So generally, it has been assumed, and I mean until recently, that steel structures are fairly safe under earthquakes and they don't need any special detailing, etc., etc. But 2 earthquakes changed this conception. So there was an earthquake in 1994 in Northridge, wherein some steel structures did not collapse actually, but many of them had damages in the form of cracks and all. And there was an investigation as to why it happened. A similar earthquake, or another earthquake which occurred on the same day, 1 year later, was the Kobe earthquake. So there also a lot of steel structures were damaged, and they were not expecting such damages to occur in steel structures. So they started investigating, and they found that these damages are due to some mistakes in the design and detailing, which can always be corrected, right? So those are the provisions which have been actually brought into section 12 of IS800, so that we don't commit those mistakes. Otherwise, the increase in cost to make steel structures earthquake resistant is very, very small compared to other structures. So, and steel also gives an advantage that it can be easily retrofitted, repaired, and rehabilitated with speed after an earthquake. Or, I mean, if you find that a particular structure is deficient, you can always retrofit the structure to make it have larger earthquake resistance, right? So those are the other advantages. So on the whole, we find that steel structures do perform well. And these are photographs from the Kobe earthquake, where variety of structures with variety of configurations. For example, the one you see on the left is a braced frame structure, which is very narrow, I would say. That is, its width is very low and it is very tall. So this structure, and the one below that you see is a parking structure with inverted V-braced frames, and the one on the right is a movement frame. So all these structures experienced an earthquake which had a peak ground acceleration close to gravity G, and they had almost no damage. We can see that there's almost no damage in these structures. So this is generally the case, but then there are some cases where we have observed damage, and then we are just trying to see that those things do not occur again. Okay. So coming back to the, so now we are going to look at how do we ensure adequate ductility and energy dissipation at various levels. So we start at the material level, and we know that basically steel is a ductile material in general. But of course, as you increase the strength of steel, like you make it from 250 MPa, you go to 500 MPa steel, what happens is it becomes little more brittle. Okay. So basically the codes like IS1893 specify the kind of materials that you can use in structural construction of steel structures. And they specify 2 particular properties. One is the elongation percentage. That is, after you do a tensile test in a coupon and the coupon breaks, you check how much it has elongated. And this elongation has to be of the order of at least 15–20% as per the material requirements. And if you have that, then you can say your material is ductile. Okay. So the other property which is very important, because generally earthquake loads are like impact type loads. So what happens is when a material experiences a sudden impact, sometimes a brittle ductile material breaks in a brittle manner. So to ensure that, we do what is called as an impact test. So there is a test called a Charpy V-notch test. So that is the CVN that you see here. It stands for Charpy V-notch test. And if we do that test and ensure that the steel has adequate energy dissipation capacity in terms of joules, it's around 21 to 26 joules. So if it has adequate energy dissipation capacity, then it is, again, we can call it as ductile. So actually these 2 properties are related, in the sense the more energy you dissipate or the more work harden you do, the steel ductility would reduce. Okay, so this is another thing we need to understand and make sure that the steel has both elongate ductility as well as energy dissipation capacity. Now we take this material to the section level, and in steel sections, the only thing that could probably limit the ductility that is formation of a plastic hinge and rotation or yielding of a section, is possibly by instability that is called local buckling. Okay, local buckling is basically nothing but a plate buckling phenomena, and this can be avoided or limited by limiting the width to thickness ratio of the plates. So once you limit these B by T values or D by T values, then you get your material ductility translates to a section ductility at the section level. Okay, then so you have sections which are ductile, but then is your member ductile, right? So member ductility is again hampered by what is called as global buckling. There are a variety of buckling modes like flexural buckling, flexural torsional buckling, etc., which needs to be looked into, and lateral torsional buckling in the case of beams and things like that. So if we can avoid such buckling phenomena, then we would also get adequate performance at the member level. Okay, and of course these members are connected with what are called connections. So at connections, we do have some elements which could have brittle failure, like bolts may shear off or welds may crack. So these are possible connection failures which could be brittle, and they need to be avoided by suitable capacity design principles, and also by suitable design and quality control. Okay, so these are that's at the connection. So once you achieve all this, then it's only a question of getting the ductility out of the structure as a whole. So as a structure as a whole, we avoid basically what is known as the local collapse mechanism, which is like formation of hinges at the ends of a column in a particular story. So I'll show a slide for that. So I'll just quickly go through what we have just looked at. That is what is the percentage elongation for steel at the material level. So here you see the bottom curve is as you look, it's a stress strain curve for mild steel. And as you load, you reach the yield stress, you have a large yield plateau. There is some strain hardening, but then eventually it fails at a large strain value, right? So this yield plateau gets you, I mean, or it enables your material to be very ductile. Okay. Similarly, as I said, as you increase the strength, normally we wouldn't want to increase the strength of steel by work hardening or adding carbon, because that reduces the ductility and elongation. So generally how it is done is by what is called as, all of you know in terms of reinforcement, it's called as a thermomechanical treatment. So nowadays we get what are called TMT rebars for reinforcement. A similar treatment can be done for steel, and we can ensure higher strength and to some extent ductility. And we can also get ductility by adding some other microalloys like chromium, manganese, etc. So this also gives you higher strength without compromising on ductility. Okay, and this slide shows exactly how local buckling in an I section or a box section happens. So as you go on compressing or applying, since it's a buckling, it will happen only when the stresses are compressive. And if you actually compress an I section with very thin flanges, you can see how the flanges become wavy, and that becomes local buckling, right? So that is how it happens. And the only way we can avoid this is by limiting the B by T values. Okay, so width to thickness ratio values. And local buckling can be reflected in the moment rotation curve in this form. So if you have what are called low B by T value sections, which are called plastic sections, then you actually reach the full plastic moment MP, and then the plastic hinge continues to rotate until a large rotation capacity 5U is reached, and that such sections are called plastic. So we would prefer to use plastic sections where we expect potential plastic hinges to form, and other places we might probably use compact sections, but we would be generally avoiding semi-compact and slender sections because they do not have rotational ductility. Okay, so how to do this? It's very simple. So you just calculate the width of your half the width of your flange divided by the thickness, and your B by T should be less than, for example, if it's a rolled section as given in the first row, it should be 9.4, less than 9.4 epsilon, where epsilon is defined again in this corner. So that is how we avoid local buckling and consequently ensure that the plastic hinges can rotate. And if the plastic hinges can rotate, then we can form multiple plastic hinges in the structure, which is eventually leads to what is known as a global ductile collapse mechanism. Okay, so that is what we get. And at the member level, both columns and beams do have the risk of having some sort of member buckling. Like in columns, we have flexural buckling or flexural torsional buckling. In beams, we have lateral torsional buckling. So if we are able to avoid these bucklings by adequate lateral support, then we do get a better performance from such elements or members. So our aim is to basically avoid the local collapse mechanism shown here on the right hand side, where hinges have formed in the columns. And we find that as a consequence, the overall structural ductility is low, whereas the collapse mechanism, which is shown on the left, where hinges form at beam ends, gives you what is known as a global collapse mechanism, which gives a more ductility and more energy dissipation capacity. So we would like to form this, and consequently our design and detailing rules are aimed towards achieving this. Okay, so that is what we are going to look at now. So let's proceed to section 12 of IS 800, where these are the sections as listed. Note that this code was written in 2007, and at that time IS 1893 was giving load combinations, etc., only for plastically designed, plastically designed structures, not for limit state design. So there was some necessity to include some clauses in the beginning, but these are now superseded by IS 1893-2016 as shown in the brackets here. So the first, of course, 12.1 is a general introduction to ductile design and detailing, and 4 and 5 talk about connections, columns, etc. And 12.7, 8, 10, 11 are the 4 major sections. 12.9 talks about EBF, which is not covered in the code itself. It just says you refer to specialized literature. But 7, 8, 10, 11 are the main systems which are commonly used in steel. And so those guidelines for such structures are given in the code. Okay. So just looking at 12.7, 12.1, it basically says that section 12 is applicable only for the design and detailing for earthquake resisting frames only. I think Dr. Rupen Goswami told you that not all frames need to be in a building, need to be designed to take lateral load or earthquake load. So only those frames which are designated to take lateral load, these have to be covered or designed and detailed as per section 12. The rest of the frames will only take gravity load, and this decoupling of gravity lateral load resisting systems is particularly very easy in steel structures compared to reinforced concrete structures. So it becomes easy to analyze and understand how such a system will behave. Okay, the load combinations are actually as per IS 1893-2016, that is 1.5 DL plus LL or 1.2 DL plus LL plus EL and so on, or 1.5 DL plus EL, etc. The last one, 0.9 DL plus 1.5 EL, is to be used only to check the overturning stability of the structure. Apart from this, there are 2 more special load combinations where we find plus or minus 2.5 EL coming in. These are required to check instabilities like buckling of a column or uprooting of footing, etc., etc. Okay, so these are possibilities. I'll explain with this slide. So the common steel structural systems I would prefer to classify into maybe 3 groups. Number one is the conventional brace frames. Number 2 are the movement frames, and number 3 are the special frames, so which I'll touch upon at the end of the presentation. So in number 1, we look at brace frames. So that is the picture on the left. So we find that we would prefer to have hinge connections both at the column base and at the beam ends. The green dots indicate that these connections are simple connections. That is, they can transfer only shear. They cannot transfer any bending moment from beam to the column. That is, the fixed end moment for the beam is 0. Okay, so such connections are pretty easy to design in steel. I'll show you some as we proceed along. So once we design a member like a frame like this with a beam and column, we find that such a frame can take gravity loads, but it cannot take lateral load. It's basically a collapse mechanism. So if I push, like the yellow arrow shows, a lateral push, it will collapse. So I need to brace this system with bracing, right? So I put X bracing here in the two directions. And then when I push, I find that the beam goes into compression, which is a very small compression. So it's normally not a big issue in the beams. Similarly, we find that what is called as the levered column also goes into compression. These are shown by the orange color arrows to show that the member is in compression. They are showing the internal forces generated. And the diagonal, which is having a yellow arrow, that is going in tension, right? So this is the brace. So we find that the load path is basically from the left end to the right joint, and then it comes through the diagonal to the foundation or whatever base, column base. Okay, so this is a clear load path, and this member which is in tension is, since steel is very good in tension, can take fairly good amount of tension, and consequently it yields if its tension exceeds its yield limit, but still it doesn't fail. It dissipates a considerable amount of energy, right? So that is how this frame behaves. The other diagonal is there only to take if the load reverses in direction, which normally happens in earthquake loading. So, but under this direct loading from left to right, it particularly goes into compression and buckles very early, right? So it becomes sort of ineffective in taking the lateral load in one direction. But if the load reverses, then this diagonal will become ineffective, but the other diagonal will become effective. So that's why we always use braces in pairs, sloping in both directions. So that is the typical, what is known as a concentric braced frame, okay? Because the beams, columns, and the brace, they all meet at a single point, right? So that's why it's called a concentric brace frame. And the other one we have, so only problem with these frames are actually very efficient. They have very good stiffness and they have very good energy dissipation capacities and things like that. But a major problem is the functionality and aesthetics, right? Aesthetics is also sometimes not an issue, but functionality, having cross braces crossing through the opening becomes a big problem. So in such situations, we would like to avoid this, and we'll go for a movement frame wherein we provide, instead of hinge connections, we provide movement connections at the ends of the beams. So what happens? What's the difference now? We don't have the brace. We still have, note that in this particular frame which I have drawn triangles at the bottom of the column to show that the column bases are still hinged. So it's only the beam to column connections at the top which are fixed, right, or rigid, right? So that is what has been done. And consequently, what happens is when the lateral force H is applied, there is an additional movement set up at the connections, which is denoted by M, apart from the fixed end movements that you have from gravity loads. And the levered column also experiences an additional force V, which is shown as a vertical reaction. So the levered column goes under compression, and the front column, which has yellow arrows, it goes under tension, right? So now imagine, like, I've designed this frame for a certain H value. Let's say the design base is earthquake, and then the H goes beyond this expected value, right? So in such cases, I should have movement capacities of connections to be more than what I would normally require. And then we find that this movement capacities are going, the frame is able to take higher movement at its connections. And then what, so that is, if we have the margin, then the connections may not break. If we don't have the margins, connections might break and your frame might go towards collapse. So we want to avoid that. So we will generally have adequate margin in the movement capacities of the connections. But what happens to the levered column? The levered column was designed for a certain axial load due to gravity. Now that axial load has increased, let's say P. So now P increases by V. So you have a load of P plus V in the levered column, and consequently, there is a risk of this column buckling. Okay, so to avoid that, we need to make sure that we also have a margin in the levered column axial load carrying capacity or the buckling capacity, and this is what we ensure by the special load combinations, which I showed you in the previous slide. And so with this, we would be able to prevent buckling of the levered column and avoid a brittle mode of failure. Okay. The last thing that could happen is the other column, which is going in tension, is not a problem because steel can take good amount of tension. But if its column base or the footing gets pulled out, then we would have a overturning of the frame, right? So to avoid that, we with special load combinations, we ensure that there is a adequate margin on the column base as well as the footing for uprooting or breaking down. Okay, so this gives us a fairly adequate ductile frame, and this is known as a movement frame. So these are the two frames which are commonly used, and depending on how much margin we have in these aspects as well as the ductility aspect, we would classify them as ordinary or special, okay, as exactly the same as we do in reinforced concrete. Okay, the third category I will talk about later as towards the end of this chapter. So this basically shows that gives you the class that ensures or prevents the buckling of the levered column under the additional axial force compression that generates due to a larger seismic force. So what it says is when there's something called a required compressive strength of a member, right? As per your analysis, you come to a value, you conclude that this column requires this much strength. So we provide a strength, and PC is the actual compressive strength of the member. So normally the actual compressive strength would be more greater than the required compressive strength. So that is something which we normally ensure. But then when the margin is less, that is actual strength is not very much greater than the required, very close to that. That is when PR by PC is greater than 0.4, then we need to ensure that the column does not buckle, and so that we will not have a brittle mode of collapse. Okay, so that is something which we are trying to do here, and by this following this class. Okay, so general comment on frame classification. As I said, we classify both concentric brace frames and movement frames into ductile and ordinary and special frames. So ordinary frames have limited ductility, and special frames have a fairly large amount of ductility. We don't really calculate how much, but we just classify them based on our design and detailing rules that we have adopted. High seismic zones and important frames we would like to rely more on ductility and use higher response reduction factors from both economical and safety considerations. So the codes generally says, as in IS13920, ordinary frames are not permitted in seismic zones 4 and 5, and also in zone 3 for structures with importance factor greater than 1. So that is something which we try to do. Now I've just revised these numbers based on 1893-2016. The IS800 gives the old numbers. So now you need to follow these new numbers. So as per the new numbers, we find that ordinary concentric brace frames, in short, they are called OCBFs. They have an R factor of 4, and SCBF have an R factor of 4.5, and OMF have an R factor of 3, and SMF have a R factor of 5. Okay, so that is how the ductility translates into a larger reduction factor, and consequently more economical design and more assured safety compared to an ordinary frame. Now, connections are very important because there's a lot of uncertainty in the understanding the behavior of connections. Even though we do some calculations and design, the connections may not exactly behave as per our calculation. So people have tested variety of connections, and what they have found is it's better to use what are called high strength friction grip bolts. Okay, and these should be fully tensioned. So the code says that in earthquake resistant frames, you should use fully tensioned HSFG bolts in standard holes. And as far as welding is concerned, they want you to use full penetration butt weld. Okay, because fillet welds do have a tendency to crack. Okay, I'll show you some cracks later on in steel structures. They do develop cracks in their welds. Okay, this is because welding introduces both residual stresses and stress concentrations and things like that. So it has a tendency to crack under cyclic loads. And it also says that bolted joints shall not be designed to share load in combination with welds on the same frame surface for a particular, what I should say, stress resultant. So, I mean, we can never avoid bolting and welding to be used together. Of course, you can avoid if you use fully welded connections, but when you use partial welding, let's say you weld an end plate to a beam and then you connect this beam to a column with bolts, because in steel, site erection becomes an important issue. So we would always try to facilitate that by using some bolted connections. So here I've shown a small sketch wherein I would lift my beam and I'll put the bolts in the web. This could be a what is called as a shear tab or a cleat angle in the web. So I put bolts and I'm transferring the shear from the beam to the column by bolted connection. Okay. Then once I have the beam in place, I can probably sit on the beam and then weld the flanges to the columns. I might use even extra flange plates, and this would give me a movement connection, right? So I have, I'm transferring shear by welds, by bolts, and movement by welds. So this is allowed, but then I can't transfer like 50% of the movement by bolts and 50% by welds, or 50% of the shear by bolts and 50% by welds. That kind of thing is not allowed. Okay, so that is regarding connections. These are just sketches showing what are the other configurations of base frames that we can have. The left one is typically called as diagonal bracing, where we have brace sloping in only one direction. And when we put a brace in the other direction, we call it X bracing or cross bracing. When we put braces in the form of an inverted V, it's called chevron bracing. You can also put braces in the form of a K, but that is prohibited by the code. Okay, so the chevron bracing has advantage that it partially takes gravity load also. So it has some special design and detailing rules. And then the last one is where I find that my brace is not meeting the other brace, or brace, beam and column are not meeting at a single point, right? So this is called as an eccentric bracing. I'll show you how eccentric bracing behaves and how it is to be designed later on. So we are going to look at only now diagonal and cross bracing. Basically, if you put diagonal bracing in two separate panels, they sloping in two directions, it is equivalent to a cross braced frame. Okay, so if you take a cross braced frame, and as I explained to you with the previous sketch, that I apply a load and one diagonal goes in compression, the other goes in tension. So if you look at a single brace, and let's say I apply compression, which is downwards in this hysteretic diagram. So once I apply compression, it will go up to, it will take some compression and it will buckle. Okay, and then if the load reverses, this buckled brace tends to straighten up. Okay, so that is what we see here. It unloads and then reloads in the other direction. It straightens up until it reaches the yield strength of the brace. So in the tension side, it always manages to reach the yield strength, but in the compression side, as it buckles more and more, due to the buckle shape, it takes lesser, it buckles at lesser and lesser load, right? So that is what happens. It never straightens up completely. So braces which are a diagonal brace, which is subjected to cyclic compression and tension, may not perform very well. Okay, so that is why we use the braces sloping in both directions, and they are generally used in pairs. And also we would like to limit the slenderness of the brace to ensure that the buckling does not seriously impair the energy dissipation capacity. So we limit the slenderness of the brace, and to avoid local buckling, we also prefer solid sections or plastic sections, right? So those are the detailing rules for typical brace. Now these photos are basically from the Kobe earthquake. They show how the braces have performed during the earthquake. They have basically buckled in one direction, you can see, and the other direction looks more or less straight. But actually, that direction also they have buckled, because earthquake load has been cyclic. We are not able to sometimes see it, but basically the braces have yielded and buckled, and then they have dissipated the energy and they have prevented the structure from total collapse, right? So that is what we wanted, and they have done their job. Okay, so this is what we are expecting when we do a proper detailing of a base frame. But this is something which was unexpected. This also happened in the Kobe earthquake. There were braces wherein the connections were not pin connections, kind of. They were very rigid connections, right? So in such cases, the brace tried to buckle, and since it was not allowed to buckle, it broke the connections. And you can see the connections are broken in a brittle manner. So it has cracked, and the crack in this second lower figure has even gone right through the column. Right? So we would like to avoid this type of a situation. So with that understanding, we'll see what the code is asking us to do. 12.7 talks about OCBF. It says these provisions only for diagonal and X-braced frames. V and inverted V to be designed as per specialist literature, because they are not currently commonly used. Normally they are used in pipe racks in some industrial structures, but apart from that, for commercial or industrial buildings, they are not commonly used. K-brace frames are not permitted. So that is something. And then regarding the detailing of bracing members, basically the code says that slenderness of bracing member to be limited to 120. This is KL by R of the brace member. And the P required should be close to the P design. That is, in other words, P design should not be very much larger than the required value. You know why? Because this brace is supposed to get yielded and damaged and protect the rest of the structure. So if you design a brace over design, that is, you may require, let's say, a brace capacity of 120 kilonewton, and you provide a brace which can take 250, right? So then what will happen is your brace will not yield until it is 250 force is coming. In the meantime, the levered column may buckle, or the beam may laterally buckle, or something will happen, and the frame may fail in a brittle manner. So since a brace is a fuse, we should not have a fuse which is over strong, right? Stronger than the rest of the structure. So we would like to limit the brace capacity very close to what is required. We want the brace to fail. Okay, so that is what this is expecting. And the bracing cross section should not be slender. So plastic or even many of your bigger angles, like let's say 100 by 100 by 6, would classify as a semi-compact section, and that is acceptable. So as because B by T is less than 15.7, but a slender section is not acceptable. Okay. So and then bracing slopes in both directions. Tensile braces carry 30 to 70% of the load, and built-up braces, the local slenderness should be less than 0.4 of the overall slenderness. Built-up braces could be two angles back to back with tack welding or tack bolting or whatever. And then we also want the connections not to fail. So connections to withstand 20% more than the yield strength of the brace, right? The nominal yield strength of the brace is Ag into Fy, where Fy is the nominal yield strength of the material, and Ag is the gross section gross cross section of the brace. So the connection is designed 20% stronger than the brace. So as I pull the brace, I'm guaranteed that the brace will yield rather than the connection failing. Okay. Similarly, the connection to withstand 1.2 times MP of the brace. Again, this is not very difficult because these sections being angles or rods or very small sections, normally their MP would be very small. So providing a connection which can take 20% more than that is not expensive. Okay. So that is how it is to be done. Next is we talk of the same brace frame. Instead of ordinary, we want to make it special. That means we want to make it even more ductile. So the provisions are pretty much similar, only for some of the green numbers you can see. Slenderness of the bracing member less than 160. Bracing cross section in this case is expected to be plastic, because we are expecting the brace to perform even after global buckling. So B by T should be less than 9.4. So it will develop a plastic hinge at midpoint, and it might probably bend at that point rather than buckle. And columns should have plastic cross section. So except for this, the rest of the provisions are all the same. Okay. And 12.9 is just one line. It says eccentric brace frames as per specialist literature. Then coming to the movement frames. So in movement frames, as I told you, we need to transfer the more than the full plastic movement capacity from the beam to the column. So there are a variety of connections which have been developed, and this leftmost one shows what is known as an end plate connection. So you weld an end plate to the beam and then bolt it to the column. So the yellow lines are the bolts. So it shows you the bolted end plate connection. And you can see there are also column web stiffeners which are shown, because column flanges tend to buckle out of their plane, right, when they are pushed or pulled by the beam flanges. So we need to provide column web stiffeners at these locations. And if the column web is very thin, then we may even need to provide a diagonal stiffener as shown in the middle figure. Or sometimes instead of this, we provide what are called as an additional web plate or a doubler plate. So that is shown in the figure C. Okay, so all three in this figure are like end plate connection. There are other possible connections. I'll show you some of them later on. But this is how the columns are, beams are given rigid end connections, which can take more than the MP, 20% possibly more than the MP of the beam section. Okay. So the second figure basically shows what is called as the middle figure, an extended end plate where the end plate has been extended upwards and one more bolt has been put. This becomes even more efficient. And if you have a very large movement to transfer, you may want to extend the end plate downwards also, and sometimes we provide a haunch. So this is a haunched extended end plate connection. So these are possible connections which can be used. Now, such connections with or without end plate, in this case, the figure shows a beam directly welded to the column, and such a connection developed a crack as shown by the green arrow in the Northridge earthquake. So there was a question as to what is wrong with this. And then they found that even though they had a margin between the connection capacity and the beam capacity, the connection failed due to some defects in the welds, etc., etc. So those things need to be taken care of. So we are not allowing fillet welds anymore. We are expecting butt welds to be done for the beam flanges, etc. Okay. And the right picture shows a crack in a column in the Kobe earthquake. Right? So these possibilities are always there. So coming to these ordinary movement frames, basically rigid movement connections to withstand 20% more than the full plastic movement capacity MP of the beam, or the maximum movement that can be delivered, whichever is less. The second part I'll explain later on of the sentence. Then rigid connections to withstand a shear of 1.5 times dead load plus 1.5 live load, whatever shear comes due to this. So I've shown this 1.5 DL plus 1.5 LL as a yellow line on the beam at the bottom figure. And due to this load, there will be a V generated at both ends of the beam. These two V's will be upwards. Okay. And when we when due to earthquake load, when the beam develops plastic hinges at both ends, so or 1.2 times MP at both ends, which are shown as the curved arrows in the figure. So due to these two curves, notice that both are anti-clockwise, right? So that they try to give a rigid body motion to the beam in the anti-clockwise direction. So this is counteracted by additional shears set up at the connections. So these are VM. So M stands for the shear generated due to the movement. Okay. So on the left side, we have V plus VM, and in the right side, we have V minus VM. And we should remember that earthquake loading can reverse. So the right side could have V plus VM and left side could have V minus VM. So basically, we are saying that the connection should be capable of taking V plus VM, right? So that is what we are expecting. This is also explained in terms of 13920 by, I think, Dr. Rupen Goswami in the previous lecture. So it is similar to that. And in rigid fully welded connections, as I showed, continuity plate should be provided in the beams to avoid the beam flange, column flanges bending or buckling outwards. Okay. Then coming to additional requirements for special movement frames, again, the first clause is the same: rigid connections to withstand a movement of 1.2 for times MP of the beam, and 0.8 times MP in case of unreduced sections. In the case of reduced beam sections. Then connections to withstand same thing, that 1.2 DL plus 0.5 LL, and then 1.2 times MP in the opposite direction applied at the beam ends. Shear strength need not exceed the value corresponding to the additional load combinations. Okay. Now, the panel zone that we have, that is this zone between the beam and the column, is called the panel zone of width BP and depth DP. This goes under extreme shear, right? So the column web plate experiences extreme shear. Now, and consequently, there is a risk of this web plate yielding in shear or buckling in shear. So even if it buckles in shear, it's not a serious problem. When the shear reverses, it kind of straightens up and then tries to yield in the opposite direction. So shear buckling is a well-known energy dissipating phenomena. But to control that and have adequate energy dissipation capacity, we may want to check that. Okay. So the code says that if your dP plus BP by 90 exceeds the individual thickness of the web plate, then we need to provide a diagonal stiffener or additional doubler plate. Okay. So that is how we make sure that the panel zone yielding ensures a ductile behavior in a special movement frame. And then, of course, beam and column sections shall be plastic or compact. At potential plastic hinges, they have to be necessarily plastic sections. That is, you are limiting the B by T values. And the next one, that is summation of MPC greater than 1.2 summation of MPB, is basically the column top and bottom column movement capacity at an internal joint should be more than 20 times the left and right side beam capacity. This depends on whether you're talking about an internal joint or an exterior joint. So, or I mean, what I should say, intermediate floor joint or the top floor joint, etc. In the case of the topmost floor, you don't need to follow this. You can develop plastic hinges in the top point of the column, that is allowed. But at other locations, we would like to have hinges forming in the beams, and this translates into what is commonly known as the strong column beam kind of design. Now, in any frame, you should always be aware that if I push a frame, it will not necessarily that it will go in the, it will deform in the same plane. It will try to twist. Okay, it will try to rotate in plan. So to avoid this, we should always ensure that lateral support is provided at several locations, column, top, bottom, etc., and beam ends, so that such things would not happen. Okay, so the plane frame will move only in its own plane. So that is something which we want to ensure. Now, as far as column bases are, I mean, a typical column base is shown here, which is a movement base. So we have a, let's say, an I-section beam shown by the two flanges on two sides and the web in the middle. So this beam is welded to this green end plate, and this end plate is anchor bolted. These are the anchor bolts going into the pedestal, RC pedestal at the bottom, and those are the nuts. And between the green plate and the pedestal, you have what is called as a grout. This is used to level the plate and all that. So we grout that part in the middle, and this is how a column base is normally done. Now, this is a fixed column base. We can also have a pinned column base. If I put the anchor bolts right at the center, I might get a pinned column base, right? So these are also possibly very, I mean, they're very commonly used in steel structures, particularly in the industrial structures. If you are designing a fixed column base, then your column base should be able to withstand a moment of 1.2 times MP of the column section. So this is our criteria which is given. And so consequently, you have to check that the anchor bolt will not pull out, the nut will not thread strip on the anchor bolt. So that's something, if the nut slips on the thread, it's called thread stripping, or the base plate may not bend and break or whatever. So all this we need to ensure that. Okay, so on the whole, sometimes this entire column may have tension, upward tension plus a movement, or maybe without a movement, so it's not pull out, right? So that also we need to ensure. So pull out capacity, and then movement capacity and shear capacity, all three has to be ensured for the column base to perform adequately. Coming to the last part of the presentation, I'll just quickly touch upon some of the special structural systems which are listed here. So we'll just go through, I don't want to read them now. I'll just go through them one by one. So the most common one is what is known as an eccentric brace frame. Now this is a V-brace frame. Imagine if it was a concentric V-brace frame, they would have used a single gusset plate, and both the braces would have been connected to that particular gusset plate, right? But this is an eccentric V-brace frame. So the two separate gusset plates are used at a distance. And what will happen is when you push this frame in the lateral direction, there will be an enormous shear developed between the section on the left and to the section on the right. So to safely transmit the shear without shear buckling of the beam web, additional stiffeners are provided. And by this process, we are able to dissipate a huge amount of energy at that location. And notice that your beam also has two braces supporting it in the middle. So the beam span has also reduced to some extent, and consequently the beam failure also is avoided. And the only thing that has to now fail is the this link beam between the two ends of the between the two gusseted sections, and that is dissipating energy by shear. Okay, so this is a common system which can be used, and such frames are known to perform very nicely during high earthquakes. Okay. Then we'll proceed to what are called semi-rigid movement frames. So we know that their connection can be simple, wherein it transfers only shear, or connection can be rigid, where it transfers the full movement that comes on it. But there could be connections which deform and transmit only partial movement, and these connections are called semi-rigid connections. So some of the connections which we see here, in the top left, we start with what are called simple connections, like a single web angle connection is a simple connection, a header plate is a simple connection. And as we go on towards right, the connection starts taking more and more bending moment. Okay, and when you come to the extended end plate or flush end plate, it takes the full bending moment that the beam can transmit to it. So in between these, we have what are called the semi-rigid connection. So the moment rotation curves look like this. So we classify up to the header plate connection, we classify it as a simple connection, and the extended and flush end plate connections are classified as rigid connections. The top seat angle and such connections are classified as semi-rigid connections. There are a variety of other semi-rigid connections also. So these connections rotate as movements are applied, but they do take some amount of movement. So a lot of work has been done to understand the dynamic behavior of such frames, and this shows one such frame which has been analyzed, and we find that the semi-rigid, this is how the response of the semi-rigid frame comes and all that. But interestingly, it was found that these frames have a larger time period. They are more flexible than rigid frames, and consequently they attract less seismic loads, and the fear that they might have larger drifts. Of course, they do have larger drifts than rigid movement connections, but those drifts under seismic loading are not as large, and they can be used to resist moderate levels of earthquake shaking. Okay, so that is something which is very interesting, particularly in our country, because we don't have very high seismic zones everywhere, right? We have zone 2 and 3 and covering most of our country, right? So in such places, we could go for a semi-rigid connections. And the important thing is we need to model the actual behavior of such connections in the structural analysis model. And so they are permitted, and the minimum strength movement capacity they are expected to have is 50% of the beam full plastic movement capacity, and this has to be achieved within a rotation of 0.01 radians. So these are the requirements as per IS1893 section 12, and the stiffness of and strength of semi-rigid connection shall be accounted for in the analysis and design, and the overall stability of the frame due to this drift that we have, that is the story drift that we have, we could add to P delta effects. So all these need to be considered in the analysis, and the safety of the and stability to be ensured. So guidelines for some of these movement rotation characteristics of these connections are given in Appendix F of IS1800. So those are only what I should call monotonic curve, but cyclic curves are not yet commonly used, so they need not be used in the analysis also currently. But of course, a lot of literature is available on the cyclic behavior of such connections also. Then there is another type of frame which is called as a truss movement frame, wherein we do give simple connections to the top and bottom chord of a truss. But notice that as shown by the two red arrows, they form a couple, right? So the truss develops end movements, and consequently this becomes like a movement frame. Okay, and as a movement frame, I already told you that there would be some additional forces, additional shear generated in the columns. So these two shears form a shear force in the beam, and this shear force in the beam is used typically at the midspan of the beam to be dissipated by some shear yielding or shear dissipating element, right? It could be a brace section like a truss, or it could be a plate or whatever. So whatever we use by that mechanism, we are able to dissipate the energy by shear yielding at midspan of the beam. Okay, so these are called truss movement frames, and these are economical because you don't have to provide the movement connections that you would normally provide in a rigid movement frame, right? So those are, that gives them economy. Then there are an entire class of structures where we use steel as well as concrete, and we call them as steel concrete composite construction. So here there are some column sections shown. The upper ones are called concrete filled tubes or CFTs. The lower ones are concrete encased sections. So all these types of cross sections have been exhaustively tested for their behavior under cyclic loading and all that, and they are found to be very fairly advantageous. So this left hand side shows the load deformation diagram, the lateral load deformation diagram of a concrete filled tube. So we find that normally if it's a hollow tube, the flanges will buckle inwards, but once we fill concrete, they can't buckle inward locally, so they have to buckle outwards, and consequently the steel tube also gives more ductility and energy dissipation capacity. The concrete, on the other hand, is also encased, so it has full confinement, so it has additional strength and energy dissipation capacity. So on the whole, we find that a concrete filled tube gives higher strength and higher ductility and higher energy dissipation capacity. So this shows some of the concrete filled tubes which have been tested, and you can see here on the right hand side how the tube has buckled outwards under axial load and lateral cyclic lateral loads, and it was found that these tubes have adequate ductility and energy dissipation capacity. The composite beam is generally made by using what are called shear studs welded to the top of the beam flange, and then the concrete is cast as a slab. So the entire slab, or a major part of it, defined by its effective width, acts together with the steel I section, and then consequently this becomes a composite beam. Okay, and these beams are known to have higher strength and stiffness than pure steel beams. So because the concrete takes the compression and the steel takes the tension, so such beams have lesser deflection due to higher stiffness, and they also have higher strength, and so they are economical. And such beams, when they are connected to columns, we get what are called as a composite connection, right? The composite beam to, it could be a pure steel column, it could be a concrete filled tube column, or it could be a concrete encased column, whatever it is. So such a construction has several advantages in terms of high speed and the low cost, etc., etc. And such connections have been studied, and they have been found to perform adequately under seismic or lateral cyclic loads. Then there are another class of structures which are called cold form steel structures. These structures are characterized by high B/T ratios of the sections. So they are liable for what we call as local buckling and other types of buckling also, flexural buckling, flexural torsional buckling, etc., etc. But if you can suppress some of those modes, as in this case we have a hollow box section where torsion, etc., is not an issue. So the only issue is here is a local buckling possibility. So the section has locally buckled, and then in spite of that, it is able to perform well, right? So this is having a B/T of around 26. So we find that such sections can also be used, and research is underway to develop other types of cold form frames which could be used in seismic resistance. This shows a two-story kind of steel frame with two beams, which are again hollow box sections, and you can see how they have developed local buckling. The interesting thing to note is that the ends have been strengthened a lot by stiffeners and all. So many people are under the impression that you can just weld a hollow rectangular tube to another column and you'll get a very rigid connection, etc. Not like that. So because the column sections will, the flanges will go inwards or buckle outwards, etc., etc. So, or the welds may crack. So they do require elaborate strengthening arrangements. So don't just weld a hollow tube to another tube and assume that it will act as a rigid connection. So there are detailing rules for transferring static loads and cyclic loads. So those things have to be followed. And one possibility is to open up the beam with a web, with an opening in the web, so that it enables the use of conventional bolts, and thereby it reduces the cost. And the thing behaves similar to another system which is called as a reduced beam section. So what happened after the Northridge earthquake was, people realized that if you weld the beam directly to a column, even though you are providing column web stiffeners, etc., there is a cracking at the beam column weld. Okay, so even though you do a very good weld and things like that, and you have a safety margin, so what they found, that was another way of making sure that the beam will develop plastic hinge away from the column face, is to weaken the beam slightly by what is called as cutting the flanges or reducing the beam section. So this is called an RBS section, and these have also been studied and their performance has also been documented. So this previous one of cutting the, what I should say, opening in a web and then drilling holes for bolt holes in the flanges also behaves like a RBS section. Okay, so then there are a new class of brace frames which are called buckling restrained brace frames. You can understand this by looking at the sketch in the bottom corner. The yellow line is a metal rod or a metal plate. You can see the similar plate here on the right hand side at the bottom of the connection, which is connected to the blue handles. So that is the core plate which is loaded, and then there is a sleeve around that, which is shown here as a tube around the core plate, and this sleeve between the gap between these two is grouted. Right now, this grouting is actually becomes easy because now self-compacting concrete, etc., are available, so we can even pour concrete into it, and then we can have a large slender brace like you see here. This brace was about 3 meters long, I think more than 3 meters long, and this brace was tested cyclically, and it gives it doesn't buckle. Only thing is, we need to be very careful with the end zones of the connections. That is, the connection parts may buckle or break. So if they are properly designed and they are not having any serious problem, this brace is able to dissipate a large amount of energy, and such braces are known as buckling restrained braces. And frames where the conventional braces have been replaced by these are buckling restrained brace frames. Okay, so this shows an example of a BRBF, as it is called in short. It's an inverted eccentrically braced BRBF. So and this frame is also will also perform well. Okay. Then coming to another system, as I told you, these steel plates, even if they buckle in a certain way, they do manage to dissipate considerable energy. They are buckling in shear in this case. So steel plate shear walls have become very much common, well-researched components, and then guidelines are available in other codes like the American Institute of Steel Construction Code, etc., where how to design such systems. Okay, so these are called in short SPSW, and these are also very commonly used nowadays in these things. And of course, we have the conventional base isolation and active and passive vibration control systems, which are also possible. These are generally more feasible for steel structures because steel structures, as I said, have lighter mass. Okay, so they become easier to install for steel structures than in reinforced concrete structures, and they are also used quite widely along with other energy dissipating systems to ensure adequate performance under severe earthquakes. So with that, I conclude my talk. I've given you an overview of how variety of steel systems can dissipate energy and perform. Only thing is, we have to be careful that they don't have brittle failure modes like local buckling, global buckling, or what you should call connection failure modes like block shear failure, etc., or gusset buckling. Those are possible modes which could hamper the performance. So if you can avoid such failure modes, then you can get a very good steel structure with the normal design without having any extra cost. So I'll close with this, and then I'd request you to ask only common questions. Don't ask questions related to your research or your day-to-day problems. Ask questions which are common to all the people so that everyone will benefit, because we don't have infinite time, we have limited time. So I'll request you to stick to questions which would help. If I missed something, I would add up with the help of your question in the form of answer to your question, or I would not be able to give you all the details of all the systems right now, but I would be able to give you a general idea of where you should proceed and how to get. Most of the, the literature are now accessible through Google and all that. So you should be able to access and get more information through that system. Okay, thank you very much.
Thank you, Professor Satish Kumar, for the wonderful lecture. So now we can go for the discussion, and the participants are requested to post their questions in the question answer session. So now the session is open for discussion. I think few questions have already been posted.
Okay, I'll look at that. Okay, I'll start with the first question. It says that in case of IS1800, table 4, partial safety factors for load, 2 cases with accompanying and there are 2 loads. One is the actual live load or leading live load, and one is an accompanying live load. This is related to basic steel design, I would say. So in steel design, they have classified the live load into 2 parts. One is a leading live load, because when you have cases like, let's say I have a industrial building column where I have a crane load at some height and live load on the roof. So we understand that both would not reach their ultimate loads at the same time. So we take advantage of this, and we say that if the crane load is a leading load, you consider the live load on the roof as an accompanying load, or vice versa. And if you check for both this and your column is safe, then that means your design is okay. Okay, I'll proceed to the next question. Why are angle sections considered as semi-compact and cold form sections as slender? This depends on their B/T ratios. Now, it's not true that all angles are semi-compact or all cold form sections are slender, but you have to calculate and do section classification as per table 2 of IS1800. Okay. Earthquake provisions in case of gantry. Actually, gantry, as I said, you will be applying, you'll be checking for 1.2 dead load plus 1.2 live load, that is the crane load or gantry load, plus 1.2 EL. So that check you may have to do, but you don't have to worry about the full load coming due to gantry during the earthquake in general, because gantry load would not come on all the frames. So the redundancy normally takes care of such issues, and it's also on a rolling wheel. So it may not transfer its full inertia force, or it may not be carrying the full, let's say a 20-ton metric ton gantry may not be lifting a 20 metric ton when the earthquake comes. So these are reasons why we don't have to take that. In plate girder, full penetration butt weld would be preferable, or fillet welds. In plate girders, you can go for fillet welds between the flange and the web, but it is preferable to have welding on both sides of the web rather than on one side. But yeah, so that is how it is. So you don't have to go for full penetration butt welds between the flange and the web. Okay. Then why people prefer BRBF? Actually, I don't know anyone who prefers BRBF over EBF. Both are equally good, so that's why they have a reduction factor of 8. Okay, both can be well designed. How to assign diaphragm of roof truss design? Okay, you may have to. What you can do is, if you're not able to assign a diaphragm action in the roof in your software, you can provide what are called roof plan bracings, and make sure that these plan bracing will be able to transfer the load from the apex to the eaves, so that the load comes on the portal frames. So that can be done. Once again, will Indian Standard provide details about KN connections? No, it's not a misuse. Of course, sometimes people do misuse many of the provisions also, but for KN type of connections for steel tubular trusses, those details right now the standards are not providing, but probably IS800 should include them in future revisions for as at least some guidelines may be required. But as of now, they are not providing. There are something called industry standards. So these can be referred like companies like Tata, Chorus and all. They provide guidelines for such connections. So you can refer to them and you can design such connection. How could we consider gravity load and earthquake load in the case of frame structures in offshore structures? Now, this would be a totally different issue because earthquake loading might translate into a wave load in case of an offshore structure. So we may have to consider that. And you can refer to courses on offshore structure designs, which are available on NPTEL for more details. Hinge column is advisable for movement frames for seismic resistivity. Basically, hinge connections can be used even in earthquake resistant frames. It's not necessary that your column base should always be fixed. Okay, as long as the column top is fixed, those pin-based connections can very well be used in seismic resistant frames. As far as material requirement as per code, how much elongation allowed? Now, typically, the codes require, I think, 15 to 18% elongation as per IS1893 code. And you also need to have the CVN number check for your material. If both are satisfied, then you can go up to 355 grade material. But beyond that, IS800 itself is currently not permitting use of higher strength of steel because of the risk of weldability and other issues. Why the permissible slenderness ratios? Yeah, OCBFs are generally having higher strength. So the slenderness ratio is limited to 120. And SCBFs, we want the braces to yield. So due to the other restrictions, higher relaxation is provided in the what do you call KL by R ratio. Specialist literature could be ASC 2016 or 2010, whichever is available to you currently. PEB structures are efficient, generally efficient to resist earthquakes. So, but again, it depends on the capability of the designer, I would say. So, and the causes that he has followed. Resulting lightweight structures will not result in uplifting normally during earthquakes because the idea of a steel structure is that it tries to resist overturning by developing tension on the windward column and the base and the foundation, right? So it is able to do that. Can we use IS800 practically since IS, what you should say, 2007 has come, IS1984 is practically outdated and it is recommended not to use that code anymore. Is there possibility to allow restricted safe movements in bolted connections to, yeah, it's possible. You can go for what are called the slotted bolt holes or roller type connections, etc. So you will have movement at that particular connection so that you don't transmit the seismic force. But then you should have some other system taking the load and transmitting it to the footings. There's nothing called special steel structural frame to be incorporated. It's already incorporated in the IS800 in the form of SCBF and SPF, special movement frames, SMFs. Angle section, while the column section only compound as well as channel can. Yeah, you can provide two angles face to face or back to back also in the column, provided you check it for all the possible buckling possibilities. That is overall buckling between the tag welds or tag bolts, etc., as you do in a laced column. Ductile detailing for steel beam to beam connection. It depends. If you are using this to transmit your seismic load path, then you may have to do a ductile detailing. In an I section, stiffener plates width and thickness ratio, how can we consider gravity? I think I indirectly explained. That is, you have to just follow the detailing rules given in section 12 of the code. For extended end plate connections, most of the literature are not considering weld design compared to bolt prime. What is the reason? If you are providing a stiffener in your extended end plate, then you wouldn't need to consider prime. If you're not providing, or if your end plate is not thick enough, then prime has to be considered in the design. So I believe I have answered this. Just 4 more open. Yeah, these 4 also I have answered indirectly because they are not directly answerable. Okay, thank you.
So thank you, Professor Satish Kumar.
Thank
and
you.
yeah, I think you've answered all the questions. Now we have come to an end for the 5-day webinar, and we had 5 fruitful deliberations on Indian seismic codes. By the distinguished speakers for our experts in the chosen field. So let us have a discussion on the final outcome of the webinar. So during the first session, Dr. C.V.R. Murthy has given an overview of Indian seismic codes, and he has come out with a critical equation, that is the future engineers. So they must be competent enough, and they must have required knowledge and skill with the right attitude. Hello?
Yeah, we're able to hear.
Yes, so sir has come out with a critical equation, like the competence must be developed through the right attitude with sufficient knowledge and skills. And the truth is that the teachers are still consider the earthquake to be a force, and the nonlinear analysis is not taught as a part of the mandatory curriculum. And seismic design codes are revised in decades. So these are the observations made in the presentation of Professor C.V.R. Murthy. So needs to be discussed anything regarding this?
I would like to add that with my interaction with several consulting engineers and all that, so what I found is many times they complain that due to such and such a revision in the code, our seismic load has increased or our cost has increased and all that. Maybe like, for example, Chennai was changed from zone 2 to zone 3. So they have a complaint about that. Or they say that this is becoming too expensive. So basically, I would like to say that the knowledge of seismic design in our country is still pretty low, and many buildings are not designed properly. So that is something which we have to really worry about. And competency or ability and attitude are also something we need to have discussions about, because many times the industry people think of economy in the at the cost of safety. So that is something which is a worrying trend, and I hope that they will overcome this, and there will be some guidelines put in place in the form of codes or other regulations, so that such practices are avoided.
And during the second day of the session, Dr. Ruben Goswami gave rationale behind the provision of Indian seismic codes. So he had given we have to make a beginning by understanding the intent of the code and the details of the clauses and strategy for implementation. So we should have a clear understanding about this, and it has to be practiced all towards a safer built environment in the country. And the earthquake safety is a mandate. It is done by the people and for the people, and need for the participation from academia and industry is a must, and the students, teachers and engineers have to contribute. So the knowledge should be shared by the academia, and the practice has to be done by the industry. So this is the outcome of the presentation by Dr. Ruben Goswami. Anything they need to be add on this, sir? And during the third day of the session, Dr. K.P. Jaya has given an impact of seismic code provisions of seismic design and detailing of RC buildings. So Madam has given the principle of ductile design why ductility is more important, and adopting strong column and weak beam strategy, and beam column joint and special shear walls, and some wrong practices in the field. And the practice of ethics in our profession is mandatory. And this wrong practices are whether due to ignorance or due to negligence. So that is a question we have to all ask for the construction practicing engineers. And anything need to be add on this? We'll have a discussion after I brief all the points discussed during the 5-day session. And during the 4th day, Dr. S.T.G. Raghukant, so he has given earthquake hazard assessment, our design PGS and design PSA given in IS1893 reasonable. So he has come out with some summary, seismic hazard map of India and displacement response spectra PGV, and an Android app has been developed to get all the details. And the effect of near field ground motion on the structures, and high performance computing and earthquake simulation. And the challenges the future engineers have to face is on analysis and design of structures on the top of the faults, and the urban earthquake engineering and forecast of earthquakes, and the machine learning on larger data that is scope of further investigations and aftershocks and on ground motion. And during the last day, Dr. Satish Kumar sir has mentioned in detail about the impact of seismic code provisions on seismic design on steel buildings. So sir has given details about the seismic analysis and design and detailing for earthquake loads and the special structural systems. And he has explained the codal provision as per IS 800 for earthquake resistant structures, and the collapse mechanism of steel structures under earthquake, and how to ensure the ductility of gusset plates. So these are all the points we have discussed during the 5-day session. So open for discussions further.
And maybe, Madam, I'll just get started.
Yeah, yes, sir.
Yeah, I look at the quality of questions, and I look at the general teaching of earthquake engineering or earthquake safety related subjects in the country. I personally think that the teaching community has to get a little more conscious and spend more time in trying to learn the subject. So in that direction, I would suggest that maybe you can take the lead, and once in 2 months, the teachers, only the teachers, no practicing engineers, no students, only the teachers can come together and raise all their questions. See, what happens is that the more is the questions, the better is our understanding of what is the level of knowledge in the teaching community. So for teachers, I would like to particularly say that if we can teach one teacher, he will teach 2,000 teachers in a case. 2,000 students in a case, right? So I would say that spending time on teachers is so crucial now, and we have waited too long, right? So it is time to start it today. If you take the lead and then build this group of people, at least in and around Tamil Nadu region here, we can build this set here. Yeah. And then if a similar colleague from, let's say, Kerala, Karnataka takes up the lead, then it will build. Otherwise, it's a hit and run, one question here, one question, one answer there. It's not going to solve the education per se. The level is not going up.
Yes.
Right? So if you have to raise the level of education, the LCM has to go up. And LCM will go up only if teachers, what Professor Goswami showed in his slide at the end, that education is not a collection of facts, it's concentration of mind. If we can change education in our colleges from what and how to why, then I think we'll make a big difference. And that is my prayer for this discussion today. Yeah.
Sure, sir. We will not stop here. We will continue. Similar platforms will be organized. The similar now it is clear that
webinars is only for teachers, not only for students and practicing engineers, because you have to sort out the teaching community first.
Yes, sure, sir. We will try to accommodate maximum teachers from all around the country from various states. We will definitely we will make it, sir.
I have a point at this.
Tell me, madam. Tell me, madam.
May I interfere?
Yeah, tell me, madam.
The thing is, the earthquake engineering course is not mandatory. We should appeal to AICT. They have given some course curriculum for the university people. So we have to project this is a mandatory course and make sure that that is learned by all the students. Now, structural dynamics is there, but earthquake engineering is not in the mandatory list of courses. So we have to put some representation to make earthquake engineering study as mandatory. Then only students will learn, then only teachers will also will be interested to learn because they have to project.
Madam, but I thought that AICT allows 20% flexibility in the curriculum that they have.
Everyone will find what I can say smooth sailing. So they are not much. Many people are not interested. Sir.
Yes.
It's a mandatory condition. People.
Yeah, if 2 earthquakes come, then they'll get started. But nobody is getting started.
Yeah, we cannot pay for it. We have to start at the earliest.
Yeah, you can't. It's important to prepare in peacetime rather than to work at war.
Yeah, yes.
Yeah.
And southern part we are comfortably sitting, so that's why people are much least bothered about.
But madam, the surprises in South India will be much bigger than the surprises in North India.
Of course.
North India will not be surprises. North India will be like, yes, we were expecting this kind of.
Yeah. Here
but in South India, for example, Killari earthquake or the Koyana earthquake, these are all beyond normal expectation in that so-called stable Deccan plateau. I think Raghukant has come, so he can say a few words on this. Raghukant, is the hazard in South India going to be a big shocker from what we are calculating, or is there a better way out?
Sir, you are on mute, sir. Please mute.
The hazard values in South India, people think that it is very low like that, but there are regions are there, some small regions like Koyana region I would have shown you. The hazard value is as high as in the Himalayas itself, like 0.5 G, 0.6 G. And it has been observed. It is not that we have got the value. So like for Koyana earthquake 1967, the PGA was something 0.63 G. So even Killari also, like from the, I showed you the data was not there, but the displacement of the boulders and others, if you see, also the values are very high actually. 0.3, 0.4 G, 0.5 G also was there.
Yeah, so I think we are mixing up frequency of the earthquakes with the size that is supposed to come. Yes. As you said, both Koyana and Killari showed more than half a G. Yes. And we are forgetting that because you're saying it's a one-time event and we are not accounting for it. But when the event happens, it will be very severe. But events will happen occasionally or rarely. That is what we have seen. Yeah, I think we can't get mixed up with magnitude, I mean, the intensity of shaking and the frequency of occurrence.
Ruben sir, you are on mute, sir.
Mute.
Unmute, sir.
Yes.
Okay.
Yeah, I'm sorry. Yeah. So the other thing that I just wanted to say is that a lot of people don't think that there are enough number of faults in this part of the country, and that is something I think Raghukant will have to take lead and keep showing that fault map again and again, so that people realize that yes, we have a potential to for seismicity in this region of this part of the country also.
Or we are at fault in South India also.
We are at fault of not showing the fault enough number of times.
I think sir, Android app may help out because everybody can understand the details about the faults and other things.
That's the main intention of the app. So that people nowadays, everybody has mobile in their hands, Android. So they can, and mobile advantage is you can touch it, touch screen, so you can zoom. That is advantage. See, computer means you see only with eyes, but here you can touch also.
Yeah. I think this we go with this living memory, and that anyway our memory is getting shorter day by day. So that is why we are losing sight of what is possible.
Raghukant, can you, if I touch a fault, can you make the phone shake a lot so that that will get the 3D feeling also?
We can make it. We can make it also.
Yeah. Madam, the second thing that I was thinking, the first thing was that, of course, focus on teachers that I had. The second thing that I want attention on is that we have not written textbooks ever since Vazirani, Ratwani, Punya, Kanetkar, and that set of 1960s. So 53rd edition, 49th edition are going on. So I pray that this, more teachers should write books, and they should start early. That is what is my second request for all the teachers. You don't think that if you know something, you write a book. When you write a book, you know something. If you don't write, you will never know, because unless you wet your hands, you get into the swimming pool, that is when you will learn swimming. Sitting on the side, everybody looks beautiful. But no, we have to get into the water. Right? So writing books and learning to write a coherent paragraph, a coherent chapter is a serious experience. And in academics, there is no other happiness than just to get this experience. Right? So I would pray that some should get started. At least the senior colleagues in the state here should get started. And they should collaborate with a few others, so that not just one point of view, but a collective wisdom is brought into a pair of covers.
Sure. So, anything else, sir? Any other points?
I've given two big points. So
big points. Yes, sir. The teacher, definitely, sir. So the major two outcomes are teachers need to be trained, and the teachers should come out and they should get their doubts cleared often.
Yeah. So first thing is the books have to come, and with that books, then you start training teachers. Once the teachers are ready, then you go to curriculum.
Yes, sir.
And once the curriculum is sorted out and the teaching resource material is ready, then you go to the vice chancellor and say, can we include it in our university in the syllabus? AICT will not stop us, but I think it is that we are not ready. As teachers, we are not ready.
I think this team can start as an initial stage. So you can support and as a support force for the start of such writing such books. I think we will initiate first, and will include more faculty members into this group.
Support will be always there. You should come out of the shell. Shell of comfort.
Yes, sir.
So, madam, there are basic courses that we do in BTech Civil Engineering, which is analysis, design of concrete structures, design of steel structures, design of masonry structures. If we can start with this 4 or 5 to begin with, I think that will be sufficient, because you don't have to teach all the earthquake concepts in all these courses. Only that incremental few have to be brought in. And that is the only effort, which is serious, because you have to intersperse in the existing concrete course, steel course, these sensibilities. So that will require a little attention.
Definitely, these points will be looked into, sir.
Yeah.
So I think we can wind up. Thank you for the suggestions given by all the expert members here, and thank you for the patient listening, and all the participants, those are viewing from YouTube channel as well as through Zoom platform. So at this time, I would like to thank our management of RMK Engineering College, and on behalf of our chairman and vice chairman and the management team, I would like to express my sincere thanks to all the distinguished speakers and the participants to make it as a grand success. Actually, this was a grand success for the past 5 days. And there were more than 4,000 viewers have seen the videos, and they were given very good feedback about the sessions. So it was a grand success indeed. So I should thank each one of you and all the participants and the management for giving all the supports for all the 5 days. So thank you so much.
Sure, madam.
So the participants can give your feedback through the online link provided. So we will, thank you. We will continue.
Please convey our regards to your principal as well as other colleagues who have helped in this.
Yes, sir, definitely I will convey the regards.
Thank you for the opportunity you gave us.
Yeah, for our chairman, vice chairman, they are very happy to have such wonderful sessions happening here. So definitely I will convey the regards, sir.
Sure.
System admin.
Thank you.
System admin, Mr. Ishwaran sir, he is here.
I think he is the main, I think.
Yeah, he is the main person behind the success.
Network.
And we have wonderful team of faculty members. We were working for this for the last 1 week continuously to make it as a grand success. So by God's grace, went on well. So thank you so much, each one of you. So we'll continue.
Thank you.
Thank you, sir.
Okay.
Hema Joyson, please stay back. Ayyo, feedback கேட்க மறந்துட்டேன்.
ஆஃப்லைன் போயிடுச்சு மேம் யூடியூப்.
ஹலோ ஹலோ ஓகே.
சரிப்பா சரி கம்முன்னு இருங்க.